In this lesson, we will be considering a very useful method for finding the real root of equations, especially equations whose roots are difficult to find. This method was fashioned by Isaac Newton and Joseph Raphson. Juxtaposing both names, the method is called the Newton-Raphson iteration method. This method is also called the tangent method because it relies on the concept of tangency. On the long run, you will understand how this works. You also need to note that this method needs an initial approximate to the root, on which all iteration is based. To find such value, we locate the interval where the root lies and bisect it. The result is what we take as the initial approximate, which we call x0 or x subscript 0. Note that it is not mandatory to pick the midpoint of the interval as your x0. The crucial thing is that you pick a value not too far from the root. After putting this in place, you go back to the formula and substitute 10 with 0. With this, we get the value of x subscript 1. X sub 1 equals x0 minus f0 over f0 prime.
Also, if you substitute n with 1 in the formula, you get the value of x sub 2 in terms of x sub 1. This gives x sub 1 minus f sub 1 over f sub 1 prime. To get the next, we substitute n with 2. Then we get x sub 3. This method continues till we arrive at the desired approximate. Let's look at the proof behind all these. Firstly, consider an arbitrary curve on the xy axis. And name it f of x. Our aim is the point of intersection of this function with the x-axis. Following the steps previously highlighted, we assume an initial approximate to the root, which we call x0. Suppose this is where the x0 is. We produce a vertical line to see where this x0 has intersection with the y-axis. At this point, the value of y is a function of x0. We can also choose to write the coordinate of that point as x0, f0. Now remember that it was earlier mentioned that this method relies on the concept of tangency. We will produce a tangent passing through this point. Also observe that this tangent intersects the x-axis. We will denote this point of intersection as x sub 1. With this development, we can establish a relationship between these points using the idea of slope or gradient. Since the gradient of a curve at a point is its derivative at that point, it holds that the gradient at this point, f0, is the derivative of f of x at x0, or say f prime x0. We also know that if we have 2 points joined by a straight line, the gradient m is y2 minus y1 over x2 minus x1. This point with respect to its coordinate is x0 f0. And this other point with respect to its coordinate is x sub 1, 0. The gradient we seek for is thus f0 minus 0 over x0 minus x sub 1. This is all we need to arrive at the desired result. Since m is the subject of formula for both equation, we can equate both equations. f0 prime equals f0 over x0 minus x sub 1. But making x sub 1 the subject of formula here, it follows that x sub 1 equals x0 minus f0 over f0 prime. This is the result for the first iteration. We use the previous value of x to arrive at a new value of x. Again, we consider the point x sub 1. Produce a vertical line to meet the function f. This point has the coordinate x sub 1, f sub 1. We draw a tangent to this point just as we did for the first point. Label the point of intersection of this tangent line with the x-axis as x sub 2. The gradient at this point is the derivative of the function at the point. M equals f sub 1 prime. We also consider these points on the tangent line. We use it to get the gradient of the line at that point also. This gives f sub 1 minus 0 over x sub 1 minus x sub 2. Since m is already the subjective formula, we equate both. We go further by making x sub 2 the subjective formula. And this gives x sub 1 minus f sub 1 over f sub 1 prime. This is again another value on the x-axis, getting close to the point of intersection of the curve with the x-axis. At the point x sub 2 also, we produce a vertical line to see its point of intersection with the function f. We draw the tangent line at this point also, and of course, it touches the x-axis at a point we will label x sub 3. When we carry out the process of gradient or slope as we did in the previous cases, we see that x sub 3 gives x sub 2 minus f sub 2 over f sub 2 prime. We see that the results are in a specific pattern. Hence we can write x sub 4 as x sub 3 minus f sub 3 over f sub 3 prime. Also, x sub 5 equals x sub 4 minus f sub 4 over f sub 4 prime. Without loss of generality, we write x sub n plus 1 as x sub n minus f sub n over f sub n prime, with n in the sequence 0, 1, 2, 3. This is the Newton-Raphson iteration formula for nth iteration. Let us quickly see the consequence of choosing an initial value that does not fit. If we consider an arbitrary function of this form, then we let this point by our x-nut. We produce a vertical line to meet the function. Then consider a tangent at this point. Recording the point of intersection with the x-axis, we observe that it is far away from the point of intersection of the function and the x-axis. Let us assume everything is fine. Now we produce a vertical line from this point of intersection, and we see that this does not intersect with the function anywhere. Hence, the Newton-Raphson iteration method fails to converge here because we chose an initial value which is not within the range of values which make it convergent. Let us wrap this up by solving two examples using the Newton-Raphson iteration method. Find the zero of the function f, given f of x is x cubed plus 2x minus 1, with x being between 0 and 1. In other words, we are to find the value of x, which satisfies the equation x cubed plus 2x minus 1 equals 0. Since we will be using the Newton-Raphson's formula, we will need to find the derivative of the function f, as it has a role to play in the formula. F prime is 3x squared plus 2. Sometimes the function could be difficult to differentiate, especially for someone who is not vast in the knowledge of differentiation. Following the process we highlighted, we get x nut by taking the half of the sum of 0 and 1, which is 0.5. Let's open this on a new page and slide in all the information we already have, the function f, the derivative of f, and the initial approximate, x nut.
Well, my guy, he said you've lost the plot, but I's the same as you. So I will stick beside you, son, in everything you do. So go on, I see your
But let's first make the function better by simplifying it. Consider taking the LCM of the fraction. Now, x sub n plus 1 equals 2x sub n cubed plus 1 over 3x sub n squared plus 2. For the first iteration, we substitute n with 0. This gives x sub 1 equals 2x nut cubed plus 1 over 3x nut squared plus 2. Since x nut is 0.5, we substitute this into the expression. and this gives the value of x sub 1 as 0.4545. We apply the same procedure to get x sub 2, but this time we substitute n with 1. This gives x sub 2 equals 2x sub 1 cubed plus 1 over 3x sub 1 square plus 2. Since x sub 1 is 0.4545, we substitute this into the expression. And this gives the value of x sub 2 as 0.4534. This is the second iteration. Let n be equal to 2. Then x sub 3 equals 2x sub 2 cubed plus 1 over 3x sub 2 square plus 2. Since x sub 2 is 0.4534, we substitute this into the expression. And this gives the value of x sub 3 as 0.4534. If we continue this iteration, we will continue getting 0.4534. This is because we have arrived at the value of x in 4 decimal places. Had it been we are to find the value to higher decimal places, this iteration will continue till the result is no longer changing. Hence we conclude that the value of x in the given interval, which satisfies the equation, is 0.4534 to 4 decimal places. One more example before we wrap it up. Find the root of the equation x raised to power x equals 5 between 2 and 3. We start by writing out the information we will need. X naught is 2 plus 3 over 2, or 2.5. The function f is x raised to power x minus 5. Finding the derivative of this function could be the problem for someone who is not rooted in differentiation. Let us quickly consider how to differentiate this function together. Since derivative is distributive over addition, consider writing f prime x in this way. The derivative of a constant is 0, so we can omit the derivative of 5. The problem simplifies to differentiating x raised to power x. Let us make this simpler by taking the natural logarithm of both sides. Ln y equals ln x raised to power x, and by the rule of logarithm, it becomes x ln x. It is easier to differentiate both sides now. The derivative of ln y is 1 over y dy dx. And the derivative of x ln x by product rule gives 1 plus ln x. Make dy dx the subject of formula. dy dx equals y times 1 plus ln x. Since y is x raised to power x, dy dx equals x raised to power x times 1 plus ln x. This is as well the derivative of the function f that we set out for. Hence f of x prime equals x raised to power x times 1 plus ln x. We employ the Newton-Raphson's formula, substituting f of x in f of x prime. Let us again consider making this expression a single fraction. We take the LCM of these. Then it follows that we have the following result. This implies that x sub n plus 1 equals x sub n power x sub n plus 1 times 1 plus ln x sub n minus x sub n power x sub n plus 5. over x sub n power x sub n times 1 plus ln x sub n. We can now work the iterations, since we have the needed values to carry it out. For the first, let n equals 0. Since we have the value of x net to be 2.5, we substitute it into the expression, and it follows that x approximately equals 2.2422. We do same for the second iteration. We let n to be 1. Then x sub 2 equals the following. Since we already have the value of x sub 1 in the first iteration, we substitute it into this expression, and it follows that x sub 2 approximately equals 2.1414. We apply exactly same procedure to the third iteration, but with n being 2.
I'm a covenanter soldier and a haughty my beliefs against dragoons and lairds who find her little Merlin thieves. But though I was an outlaw when I started,
it follows that x sub 3 approximately equals 2.1295. We do the fourth iteration also. We substitute the value of x sub 3, and it follows that x sub 4 is approximately equal to 2.1294. We proceed to the fifth iteration, where we take n to be 4, just like any other. We substitute the value of the previous iteration, and it follows that x sub 5 is approximately equal to 2.1294. Since the result of this fifth iteration is exactly what we have in the fourth iteration, we can be sure that further iteration will also have this result. Hence, we can conclude that the value of x that satisfies the function is 2.1294 to 4 decimal places. In this lecture, we have seen how to prove the Newton-Raphson's formula and how to apply it in solving equations with real root. Without doubt, you have learned something new today. Do well to like, comment, and subscribe to this channel. Thank you very much.